Welcome to our BNS on Aerospace and Defense podcast series. I'm Pat Hindle, Media Director for Microwave Journal's Signal Integrity Journal. I'm joined by our host, Brian Goldstein, President, Analog Devices Federal, and Vice President, Aerospace and Defense Group at Analog Devices, and also Sean Darcy, Senior Director of Aerospace and Defense at Infineon. Welcome, guys.
Thank you, Pat.
Hey,
Welcome,
Pat.
Mark.
Yeah, and we have a special guest here. Mark Hepburn is Director of Product Management at Cadence. Welcome, Mark.
Thank you. Thank you. Pleased to be here.
So there's been a lot of talk about model-based system engineering. It's been a hot topic and been developing these days, especially with the advent of AI technology and machine learning kind of getting into the case there too. So I thought that'd be a great subject for this episode. And Sean, why don't you start off? Like, what is MBSE?
Hey, thanks. So, Mark, thanks for joining. Glad to have you here. So I think model-based system engineering means maybe something different to different people. So I'd like to hear how you define it and what do you see it as in a way it contributes to our engineering design process, and then maybe tell us about some of the advantages and disadvantages.
Yeah, so I think you're right. Model-based engineering, model-based systems engineering definitely has a perspective depending on who you are and where you are in an organization. At least that's been our experience. And I would also say a lot of people don't quite know what it is yet. We get this question all the time where they're saying, hey, where do we start? What is model-based engineering? From our perspective, I like to view it as it's digitizing from the requirements all the way through the actual implementation, but enabling that with pervasive use of simulation and analysis in a very iterative form, which I don't think is fully in place today, especially in many of the spaces that we work in. For example, consumer electronics is an area that you might not think model-based engineering is approaching. It's absolutely there today, but they're trying to figure out how to accomplish it. So that's kind of how I would look at it. And I think a big part of it is establishing that continuity, not only from the simulation and analysis, but the continuity between the different tools and the different domains. How do I move information between those two domains is a key part of the MBSE approach. That's my 2 cents, kind of how we see it.
This is a very broad topic, and so I'm trying to wrap my head around what you and Cadence do. So how do you start? Can you kind of walk us through the process of setting up a system? And again, when you go into a specific domain, how do you start? How do you get the information that you need? Do you need to learn about that industry? Do you need to learn about that application? And then ultimately, once you build the model, how do you verify?
Yeah, good question. So yeah, the getting started, I think, is one of the biggest challenges. It's certainly what our customers struggle with, trying to move along. And I know it's trite, but it starts simple is basically what we're seeing people do. So I go from kind of the document approach that they're starting with, right? So in our world, people are starting with block diagrams, trying to describe the system and capture their connectivity and functionality, right? Today that's done independently. It's done in a document. It's a written requirement. So step one, we're like, can you just start to capture from your systems engineering standpoint? Can you start to capture the system architecture? And can we incorporate that system architecture in our implementation domain? Because that's largely where Cadence sits. How can we consume that system architecture as the starting point? That's kind of the next piece, kind of that top-down flow. And then the next piece that we tend to approach with is, how do I cycle back up? Because you now have two independent design processes, if you will, right? You've got the system architecture that started somewhere, but it's going to continue to evolve over time. And you've just done a handoff into implementation, let's say. Guess what? It too is going to continue to evolve. So how do I sync those two back up? And that's kind of the feedback loop. How do I bring back that as architected and compare that to the as built? Is a real simple place to start, but actually provides a lot of value because it gets people into that model-based approach, but it gives them real value because they're communicating between two domains that were traditionally disconnected, or at least over the wall. And that gives you the framework now to, I think, answer your second part of that, which is, how do I verify it? Now I have the model to start hanging off different steps of verification. At the beginning, it might just be a requirements verification. Have we captured what we wanted? But as you get further in that implementation model, I can now feed up simulation results and compare that back to a requirement. Which again, if it's done in a document-based approach, really hard to do because somebody has to infer that. If it's in a model-based approach, I've got a parameter in the system model, I've got a result in the implementation or analysis. I can now do an empirical, comparison between the two. So that's one way to approach it. We're just trying to take a very pragmatic, step-by-step approach because it's a huge, broad area for people to work in.
Do you start by scratch with your own ideas, or do you find that it's mostly customers coming to you with a specific need?
In terms of the model-based approach, is that your question?
And developing your toolkits.
It's a mix of both. So we have some customers that are very far ahead, very mature in their model-based approaches, and they're coming to us with, how can you enhance this? Can you give us access to this API or this piece of information that they can incorporate it into their overall approach, right? And we have others that are, just as I walk through, they're going, we know we have to do this. Do you have any advice as to where to start? From our perspective, keep in mind, obviously we focus on the core electronics aspects of things. Sometimes those questions go beyond what we deal with, right? What happens in the mechatronics domain, right? We can only go so far, of course, and that's where we start to collaborate with other partners in the industry because, you have to. The customer's trying to solve a bigger problem than any one company has the ability to address.
I guess, something that's probably a good question to ask on that is, you said, how you actually advance from paper all the way through. What's the journey from somebody? It starts with basically they're doing Excel, they're doing Visio, and then how does that move to, some true model-based design, model-based engineering and simulation?
Yeah, I'll tell you what we're seeing right now, and there's a pretty good base of it. So there are some tools out there, not necessarily from Cadence, where a lot of people start, right? And it is things around the SysML approaches, right? That gives them kind of a kernel to build around. And then there's tools that sit on top of that help author SysML, right? As SysML, derivative of UML, of course, not exactly human readable. But it is very declarative. It's very formal, provides a lot of benefits. So that's where we're definitely seeing a lot of people starting there. And the tools that are built around that give us the facility of continuity of the model to move it from that high level definition into perhaps the implementation, because there is a structure there. So what we're seeing largely is people adopting that type of approach. As part of the model base. So they're not generally just going from just Excel directly trying to build something new. They're usually trying to bring in a new approach to systems engineering, usually around a SysML type environment. And then this is an area where, in particular, Cadence, where we decided we needed to partner to start to address some of that, because we don't have that overall system perspective. When you cross domains, right? Going into mechanical, when you're going into the electromechanical, the structural domains, we need to interface there, but we don't necessarily have that whole picture. So a higher level solution has been something that we've opted to partner on to bring that to market.
So is that the goal? Is the goal to take that system level view and then bury down into the details of the electronics, in the mechanical and the thermal, and connect that high level model to the very specific model?
Yes, ideally that's the grand vision that we see most people trying to chip away at. How can they have a complete picture of the overall system, decompose that system into multiple systems of systems, if you will, right? And refine that. Eventually you get to an implementation model. Along the way, one of the things we were seeing in that kind of path you just described, that kind of top-down approach, is the exploration of the model, right? So people may come in and say, hey, we need to do a full custom ASIC for this piece of functionality, versus perhaps an FPGA, perhaps microcontroller with software, right? very different approaches, and then they compare that back to their internal capability, right? Do we have a software repository that can solve this problem already? And these are the systems engineering challenges that kind of get broken down as they refine. That's the top-down approach, but don't forget about the middle out, which I think is where a lot of people ultimately start. They have IP, they have expertise, they have an existing design. In a lot of cases, what's going on is, how do I go middle out, which is, how do I take my existing repository of content and, turn that into a derivative product? And that's just a pragmatic way of where a lot of customers, especially in the consumer space, need to start, right? We see more the aerospace, defense, and automotive tend to approach things a little more top down, just their way of working. But the consumer spaces, we tend to see a little bit more middle out, and that's, I think, largely because of derivative product and really short windows, right? That they're trying to build to.
Well, a lot of us come from the device world. Is there a bottoms up? I mean, there's always, individual device models that we try to put together, but, they have to interact and make a system. So is that also a method, or because that seems common from the device people?
It's definitely something that we're working with and trying to engage with the semiconductor providers today, because in order for oddly enough, for the model-based approach to work, you kind of need the models. And that's an area that we see a lot of value, that is derivative value directly to the customers, right? If they can go to a place and get a complete picture of their piece of silicon, whether that's heterogeneous design and everything around the chiplet, whether that's a packaged device and all the models that surround that, so they can do their signal integrity analysis. Back to your question about how do I verify? Well, to verify, I need the models, right? So that's clearly a challenge we're seeing. I don't think it's been resolved yet. The models are very point to point, I would say, especially in some of our spaces. If they got big enough wherewithal, they can work with the vendors to get that content they need, but a lot of times they're sorting it out on their own.
Yeah, I want to dig into that point about models and IP a little bit more, because I think all of the simulators, ideally they would have models of standard products that exist in the market. Mm-hmm. And so some developers of products building good models, that's part of their strategy, so that their customers can very easily pick up their products and use them. But where you're going is to build an even bigger ecosystem, where you've got these models, or where you can build models of models. But yet a lot of folks who are building those lower level components, they see those models as perhaps their own IP.
Yes.
That differentiates themselves in the market. And so how do you see all this being able to get to where ideally you'd like to?
You're absolutely correct, right? That the IP protection and the models can expose too much, right? So we're working on some strategies with some of the component suppliers, where we're saying, look, can we get a black box model? We can't see inside it. It can provide stimulus, provide a result, right? Effectively the same if you had the device and you could test it, right? Conceptually speaking. We're getting a little bit of traction there. And what's driving that traction, I believe, is because of the model-based approaches that are becoming much more pervasive, and this need for analysis continually through the process. I believe that the manufacturers are now starting to see that their ability to provide different levels of models with their applications starts to become a bit of a competitive differentiator. I think that's what's going to drive it, right? I'm going to pick a device more often. Again, in many of our spaces with the fast turnaround time, I'm going to pick a device one over another if it's got the models I need to move forward. Right.
So just another question about the models, because you said something interesting about the black box and data. Does a model actually need to be a model, or can it be a set of data?
It can be a set of data.
It can.
Yeah, it can be a set of data, right? If you look at something like an IBIS model, internally, it's basically a table of results, right? That gets shipped along, right? So it doesn't necessarily have to be a detailed SPICE model, for example, that exposes internal content. So I think that's a good observation.
So I guess to rewind a question, what do the models actually look like? We know IBIS, we know Spice, there's probably Sabre models. What do they look like as far as the models we provide the system? And what do you think some other constraints besides what we've already talked about would be?
Yeah, I mean, I just go down the different multidisciplinary domains, right?
Right.
Thermal, right? Thermal representations of the design, which generally involves some notion of the 3D geometry, right? To be able to bring that in. The model extends to not just the electronic component as well. I mean, you need to start to understand in the context of the system, the model of the enclosure is important, right? Is how does the cooling actually work, right? What kind of shielding is there, and what's the shape of that? All these things, require models. So not only are the models electrical models, but we're growing and more increasingly needing the mechanical side of that modeling world as well, right? And there's some standards out there that help. In the 3D space, things like STEP can be useful. There's different exchange mechanisms out there that can be useful, but I think more still needs to be done to kind of expand that definition of what a model is.
Who do you see leading that charge, and what would you guys like to see from, the semiconductor manufacturers to help, accelerate probably the adoption of model-based engineering?
Yeah, I mean, I would say electronic representation of everything, right? That would be the big ask. We know the information is all there. We understand there's IP protection, and we're willing to work to figure out what is the appropriate solution there. But the goal is, I'll put this real simply, coming from largely the PCB world, right? So my background comes from there. So much of that world is based today from the device manufacturers on a PDF data sheet. That's the exchange mechanism. That is not useful in a model-based approach, because the first thing somebody does is they take that PDF data sheet and they translate it into something much more technical that drives the tools. So I'm just using that as an example, but all the data is there, right, inside the companies. It's how can we work with the ecosystem to figure out how do we appropriately and securely make everything in as much possible out to that ecosystem in a digital form, not a document form, not a PDF, right? So that's kind of the big ask. I know it's kind of broad, but there's no one specific thing, right? You go to a connector company, they need to supply the 3D model, the connector, and the analysis around it, right?
This is such a complicated topic that I'm trying to wrap my head around. So I want to know kind of what is the state of the art? What is the state of the industry right now in terms of bringing RF and digital and software and mechanical? What is the state of the industry right now? Because historically, when I would design, each of these areas would be done independently of each other, and then brought together, almost with a pen and paper. And so, what is the state of the art right now?
Unfortunately, I don't think it's changed too much. Yeah, I think there's just a lot that process still is very pervasive, and I think what's occurring now is because most of our customers are no longer just designing a little widget. It turns out that widget is a system in and of itself, and is usually part of a bigger system, right? Everything's connected now. So they have to model the software. They have to model not only the RF, they got to model the protocol back to whatever the receiver is, right? These complexities, I think, are forcing those barriers to come down, but for sure, they're still there, right? You still see that over the wall. Here's the PowerPoint of what we're thinking. Can you make it work?
So what are we doing now that we couldn't do 5 years ago or 10 years ago? I see, when I look on your website, I see three-dimensional models with SIPs and chiplets, and where you're doing combining 3D simulations with 2D simulations with thermal simulations. So where are we now compared to, say, 5 years ago or 10 years ago?
So first, I think it's the pervasiveness of simulation and analysis. There's not a single one of our customers that isn't trying to grow that part of their competency, right? And then I think on top of that is just availability of compute resource and scalability that can enable it, right? A lot of these things just couldn't be done at scale 10 years ago. The capability simply wasn't there, or you had to build a massive infrastructure. But now there are strategies and capabilities that we can even do on demand for customers, right? So that's difference too. They can plug in when they need it, right? So the whole consumption approach from a business model standpoint has been shifting too across the industry, and I think that makes the analysis much more accessible to the communities where it wasn't.
I think the thing I've seen in the last few years is that all these software used to be the thermal system was different from this simulation, but now companies have bought them, put them together into a platform like Cadence and even other companies. And so you can share the models between each other now. They're connected, and before they weren't, and it was disconnected.
So they may be separate analysis, but at least it's using the same basic model.
Use the same platform.
Between platforms, you can do all that easily without having to manually do it.
And the other thing is, some of these simulations would take days, if not weeks. And now
compute power is crazy.
Compute and parallelism. The other piece too, I would say, is kind of like I mentioned before, continuity of the model. So a lot of what we're doing is we're starting to now make analysis not necessarily a separate thing, right? You still have that for very specific areas, but how do we bring analysis, left shift it directly into the design cockpits, right? So that's a difference where, there was always somebody else that did the analysis, right? And we're trying to bring that right to the design engineers and make it consumable for them, which is hard. Definitely hard.
It is. So I guess a question on that is, how far away do you think we are from, for example, being able to simulate very accurately, like a complete, phased array radar, like the ANISA, where we actually would understand, everything from thermal, variability all the way up through quality of power, et cetera?
Oh, that's a good question. Ask me to try to use the crystal ball here.
Yeah, we have a little deep ball here.
You watch the Jetsons, right? You should know what's going to happen.
That's right.
We're here.
A little bit of Star Trek. Yeah, there you go. I don't know if I could put a timeline on it, but I mean, what you could say today is, I think the big pieces are there, not necessarily all connected yet. That's one of the things we're working on really hard, is to connect all those things together. I think there's still, when you get into some of the simulation and analysis areas, it's still very niche. And the expertise is still very niche, right? You get into, some of the things like around, for example, CFD, right? Hey, it's all CFD. No, it's really not. It's, there's an engine for this very specific solution. There's another engine for this very specific solution. And they really can't cross, because they're so specialized, right? So I still think that's there. I think a lot of work is still needed in that piece. What I do think is starting to occur that will drive these things together is companies are looking at their overall design and analysis workflow, if you will, from end to end. And I think that's a change. They're no longer looking at it as just, this is how I do this part of analysis. This is how I do this part of design. They're really starting to look at it from end to end. And they're starting to apply not only model-based approaches, but simple block and tackle approaches of life cycle and workflow management.
Oh my God, you said workflow. Brian,
I said workflow. Oh no.
Oh man, the workflow thing starts. So hey, so thinking of a workflow, I kind of wanted to, we're actually doing some of the simulation, if you could contrast some of the challenges, like we talked about an RF and microwave type, design, but when you look at actually the components and the parts, maybe contrast, RF components versus how do you get accurate power, are those the same challenge? Do you see those different?
I think it largely goes back to what I was mentioning before is, how do we make and expose from the device manufacturers? How do we do a better job of getting that content that was already used internally to develop the device and make that available? Because I think a lot of that data is there. It's just for good reasons right now not made available, right? And I think that's a challenge the industry has to get over, somehow to solve these problems. We've seen this in some cases, where it can be addressed. Some manufacturers will provide certain capabilities and models and things like that along, but it's still not very pervasive. In the discrete world, just getting people to provide information about the PCB footprint is hard, right? A really simple thing like that, and it's still hard to get that information out. So I think that's kind of where some of the challenges lie.
No, definitely. If I can switch subjects, I want to ask you a little bit more, kind of talk about, when you design full systems, many of us have always had to be concerned about design margin, and we put a lot of margin in our systems. So, I mean, how does model-based system engineering help minimize that, right? There's a cost both in dollars, time, power, efficiency, et cetera, because we're designing in all this extra margin. What are you guys doing to, help address that type of issue?
So I think where that comes into play is, it's not directly model-based, it's an artifact of what model-based starts to enable, is you need to collect information about the entire design process all the time, because all of that data is incredibly useful. So every time I go through an iteration and an analysis, that needs to be captured and tracked and then mined later on for better decisions, because otherwise, how do I improve? So you might not be able to improve that margin on the very first time, but as you iterate, you can start to understand the choices you've made and use your past experience. And I think a lot of that data today is not consolidated and not mined. And if you have a model-based approach where you do have a more structured approach of getting from point A to point B, then that data becomes all that much more useful. I can use it to guide me through should I have done that analysis? Could I have tightened up this constraint? And I have empirical data that shows me that I could have. Today, I think it's a lot. You run it through and you go, did we make it? A little ad hoc, I think, today.
Earlier, you mentioned that design teams were starting to really focus on their design flows and their timing of their design flows. And this just came up for me over the last day or two. And it has to do with how the hardware designers and the software designers work together. And historically, the hardware had to be designed and put on the table before the software designers could even start.
Yeah.
And now they're talking about digital twins and how do we get the hardware designers to put together models so that the software designers can get started while the hardware designers are working, and even the customers can get started maybe even years before the hardware is available, so that a lot of this legwork can be done much earlier. And so how does that align with what we're talking about here?
Yeah, I think that's a good point in terms of the general model-based approach. So if you head down high-level model-based, right, you're starting perhaps top-down, that's an easy way to approach it. You may create some basic functional models, which in fact could be enough information for the application level APIs that could be started much earlier, right? Because they're not as bound to the detailed hardware. So you start to capture that. That starts to give you insight as to what your perhaps lower level capabilities might need to be. So I think there's some capability there. And then of course, the continuity of model. If I create, for my next generation SoC, if I create a system C model for that or some component, how can I make that model available to other people? Because again, it's there. Somebody's probably created it, but how do I make that available? We are seeing some of our customers starting to push into that. They're going, we've created this model. How do I now make it available throughout at least my organization? And it's along the topic you just brought up. It's the earlier software development. So they can start to understand, will the software even work? Can we even start that development now, right? And building it against perhaps a C model earlier on is possible. And a lot of times the content's there. It's just not made available across domains yet. And there's work to do to make that happen, of course. But I think a lot of it is just the communication between the teams and having that top-down approach where we know that there's a system that's going to be software. You may not even have that defined up front.
And the question that we're talking about is creating this digital twin while it may make writing the software start earlier, is it extra work for the hardware team that maybe isn't necessary? And so, or do you need the hardware to exist to even create an accurate digital twin? And so these are debates that we're having right now.
True. It's true.
Yeah.
It drives a lot of reuse just for that reason. So we've
Yeah.
got to go back and develop at least the digital side on what we already have.
I gotta wonder too, what's going on is the term product realization comes to mind. So if you're purely a hardware company developing just a device, that might be a little more difficult of a challenge. But from a company building a new EV, right? They're starting to look at it from, it's not necessarily, I have a hardware group, and how does my hardware group impact my software group? They're looking at it in totality. How do I get my product out the door? And yes, if there's more effort for the software team up front, so be it, right? If that helps the hardware team and vice versa. So I think they're starting to do optimization more at a system level and not at a particular domain level, because they have to. They have to look at the entire solution end to end. And I think that's another change in mindset in the systems companies, right? That we definitely see. Right, and we see a lot of that with the EVs. We see a lot of that in the consumer electronics. They're starting to really look at the product realization, not the individual domain realization, and it's starting to impact us. Right, these are the questions we're getting asked. How do you plug into mechanical engineering? How do you plug into software engineering? Things that were always kind of secondary in the past, right, are really becoming the forefront of what we're being asked to do.
No, very true, very true. So something that Cadence actually has a lot on their website. They talk about AI and artificial intelligence. How do you see that, like generative AI, playing into the model-based engineering?
Yeah, I think it's critical. So first off, by having the model-based approach, you have structure around your information and your data, right? That you have. That's critical to creating a repository for AI and ML to take advantage of. So, some of the things along the way, applying things such as large language models to the requirements, and then intersect that with your RTL design flows, right? I don't know if anybody's, toyed around with Chat GPT these days, but, you can ask it the right code and it kind of does. It's not perfect.
It does, yes.
It gives you a really good starting point, right? And why are those things in the context of a model-based approach not applied in the electronics design flow, right? And that's definitely an area of growth. And I think the AI ML capabilities are critical to that. But you also need the data and the corpus of information behind it to be able to drive that. So it's a little bit of a give and take. Got to capture the data in a somewhat structured form, and then take advantage of the AI ML technologies that are out there today. Our customers have a huge pile of IP, right? It's basically just locked away on servers somewhere, right? So just inside their company, how can they make use of that and bring that back into the overall design approach?
I'm going to turn it over to Brian because he likes to ask his George Jetson question on the future and what maybe the next 5 to 10 years brings.
Yes, we have found on every topic that we've had that George Jetson and his family and Spacey Sprockets has predicted everything that's happened in the industry so far. So I'm going to ask you, based on your memory, you talked about where we've been. The question is, where are we going? What advancements? Not 20 years from now, but just within the next 5 years, what do you think is going to be sort of monumental in the next handful of years?
Yeah, I actually think the intersection of AI, ML, large language models, obviously related, and access to high levels of compute and high levels of storage I actually believe we're going to get to the point of describing system functionality almost from what it is I want, and getting perhaps not the entire design, maybe that's 10 years from now, but in kind of the 5-year time frame, getting a really accurate cost model immediately popped out so people can understand what this will be cost, feasibility. I think that's totally doable, as well as the actual generative design and getting that first pass design that now your experts can take over and tweak. And I think in 10 years, I think that becomes much more automated. Now, what I'm not trying to account for there is what new big piece of, implementation technology comes down and perhaps might disrupt that, right? How does that all factor into the design process? But I think largely for where we're at today, I think that type of going from requirement to a starting point design or implementation is very feasible. And we're already starting to see evidence of that today in the generative AI spaces. So I think that's probably the next big exciting thing. And that's going to free us up for a whole new area of innovation, right? Things we can't think about right now because we're worried about all the implementation details to get things, with what we already know how to do.
Well, perfect.
Sounds good. Well, thanks, Brian, Sean, and Mark. Thanks for being our guest today, for your insights on model-based system engineering. I think it's been a great discussion. If our listeners have any other topics they'd like us to cover, just email me at phindle@mwjournal.com. Thanks for listening, and keep an eye out for our next episode in a month or two from now.